Welcome to topic 12. We've already looked at pop and ow, and now we're going to look at some special segments and circles. So what I look at is here's some chords. Now it says if two chords in a circle are congruent, then the central angles will also be congruent. And what that means is if I connected these, that if these chords are congruent, these angles are congruent. Now if two central angles are congruent, then the intercepted arcs are also congruent. Now by the law of syllogism, because I can always cross out the middleman, if you remember right from way back when, in Unit 1, I can cross out the middleman, and I'm left with if two chords in a circle are congruent, then the intercepted arcs are congruent. So that tells me that this arc is also congruent to this one. So let's go ahead and look down here. I know that since these two chords are marked congruent, that's what those little hash mark means, that they have to be the same. So x is 65. Now number 2, central angles pop out to arcs, and this arc is also 40 because of the congruent hash marks. Now in an entire circle there are 360 degrees. So if I take away 240, 40, and 40, I end up getting 40. So x in this case happens to also be 40 degrees. So if I move on to the next example, I'm always looking for what's congruent. So since these two are congruent, this is 115, this is also 115. So I'm going to add these up or take them away from 360. And when I do that, I get 42. So this arc is 42, which means that angle, because it's a central angle, is also 42. Now, congruent arcs mean that they're going to be the same. So how many x's do I have? I have 3 x's plus 84 equals 180. I'm going to subtract 84 on both sides, and I get 96 equals 3x. I divide by 3, and I get 32 equals x. Now finally, number 5. This is a central angle. It pops out. Now I have all these congruent arcs, so I can put x's there. So how many x's do I have? I have 5 x's. And all together in a circle are 360 degrees. So I'm going to divide both sides by 5, and I get x equals 72. So next, let's look at 2 other properties. Congruent chords in a circle are equidistant. That means if AB is the same as DC, then I know that EP is congruent to FP. Now also down here, if I look, the radii are perpendicular to the 2 chords. So when a radius is perpendicular to a chord, it bisects the chord, which means to cut into 2 congruent pieces. So this is equal to this, and this piece is equal to this piece. RT is not the same as AE. So let's look at some problems dealing with these properties. Number 1, it told me, and I'm going to probably highlight it so I can see what's going on here, AB, from A to B is 12. Then it asks me, and it says, what is DC? Well, DC is this entire segment. Well, I know that since they're the same distance away, that those segments have to be equal. So it's 12. Now, EC right here is congruent to this one. So it happens to be 6. Now if I look at number 2, EC is 4, AB from A all the way to B is 8, and FG is 3. So since this is 4, this is also 4. Now these two chords are congruent because from D all the way to C is 8. So that means that they have to be the same distance away from each other. So FE equals 3. Now 3 is where it starts to get fun. From A to B is 14. That means that each little piece is 7. EC is 6. And it wants to know, what is EA? Well, this is what I mean by it starts to get a lot of fun. They like to throw shapes inside triangles, or inside, they like to show triangles inside many different shapes. So now I have this right triangle sitting here, and I did rotate it a little bit. A to C is 7, 6, and this is x. So I'm going to use my Pythagorean theorem. I need to know which one is my C, which one is across my hypotenuse, across from the right angle, equals 7 squared plus 6 squared, which is 49 plus 36 is equal to x squared. When I do that, I get x squared is equal to 85. I take the square root of both sides, and x equals the square root of 85, which is about 9.2. So let's go ahead and look at the last two problems. If I look at 4, AE is 24. EC is 14. And then it says, how big is AC? And I can see that right triangle sitting right there. And I need to label my C, my hypotenuse. 24 squared equals x squared plus 14 squared. 24 squared is 576. 14 squared is 196. I'm going to subtract 196 on both sides, and I get 380. So I take the square root of both sides, and AC is the square root of 380, which happens to be about 19.5. Now, for AB, it's twice as long, so I could say 2 times the square root of 380, or 19.5 times 2, which is just 39. Now, number 5, it says CB is 15. DF, the whole thing, how big is it? Now, because there's a little circle, my radii all have to be the same, so I know they're equidistant. So if this is 15, this is 15, this is 15, and the whole thing is 30. So we have one last problem. I love when they hide triangles, especially right triangles inside of shapes. AE is 16, and the measure of angle A is 40. So here's what I'm sitting with right here. I have 16, 40 degrees. I know this is 90, and it wants to know how big is AB. Well, in order to know AB, I need to find AC. So that's where I'm going to put my X. Now I can't use the Pythagorean theorem because I don't know what CE is. So if I pick this angle and I label my opposite, my hypotenuse, and my adjacent, cross out my O, I know I'm going to be using Ka from SOHCAHTOA. So cosine of 40 equals x over 16. Since that 16 is in the bottom and the x is on top, I know I'm going to multiply, and I'm going to get 16 times cosine of 40. Make sure I'm in degree mode, which is 12.5. 3. Now I'm not done. Only AC is 12.3. CB is also 12.3. So when I add those together, I get 24.6 for the entire segment.